Peter. We have today Peter Veerman from Oregon, no, Portland State University in Oregon. So I believe that it was Oregon University. No, Portland State because of in Oregon. And this will be a presentation. I'm very happy to be Peter here of the, I don't know whether it's called also in English, the Ruffini-Abel theorem. Mm-hmm. Also in English? Yes. Abel-Ruffini, the Ruffini-Abel. We are Italian, so in Italy is Ruffini-Abel.
No, Abel-Ruffini.
I don't know. The Abel-Ruffini and the Ruffini-Abel theorem.
Oh, you know.
I read Abel-Ruffini.
And so, if I understood well, this was a proof suggested for the first time by Arnold. Vladimir Arnold, that I hope that you know. So, a great mathematician, a great physicist, a great scientist. So please.
Yeah, thank you very much. I won't be using the microphone. I don't think I need it, but if you can hear me. First of all, a disclaimer, I am not a number theorist. This is from a book that I wrote because I was unhappy with the book that I had in a course on number theory that I taught. And I thought, oh, even I can write a better book. And that was a one-term course. So then you start writing and it's kind of hard to stop. And so it became a full-fledged 3-term course. This is the last chapter of the book that I'm going to do. The book is going to come out by Springer Nature sometime early next year, I think. Let me see if I can do this. My name is Peter Veerman. I work at the Math Stat department of, I'm actually affiliate professor of physics and physics as well. I forgot. Portland State University. Previously, I did my master's degree in Holland in theoretical physics. At that time, of course, high energy physics, we had very famous professors in high energy physics, Veldman and Hoofd, and I talked to their students and I asked, what do you do? I was curious, what do you do? And they would show me these huge computations. It was all perturbative, huge computations. And I said, oh, that's great, but what is the point? And they would be stymied sometimes. And I thought, oh, this is too complicated for me. I don't want to be computing all day and then not knowing why. And so I decided I was going to go somewhere else and do dynamical systems, which at that time in the mid or early 80s was still relatively new. So I ended up at Cornell doing a PhD there with, among others, as mentors, Mitchell Feigenbaum. And from there on, I went around the world, in Brazil, among other places, but also in Spain and even a year in Greece. Usually in smaller places where you kind of do what comes by your desk. You don't have a big research group with very powerful people and lots of grants. So you do what you can do. So in the course of my life, of my scientific life, I've been also I'm a person who likes to look at new things. So I've looked at problems of flocking, always dynamical systems based, but also problems in pure topology. I'm happy to talk about that too. But flocking, I can't remember, social processes that you can describe by mathematical means, and many other things. I currently, my favorite course to teach is actually game theory for non-mathematicians. And so that's that's a little bit about my background. So this is, the motivation for this book is as follows. Beside the course that I taught, I'm aware that, or at least in my case, but I think for many people, you come into these math or physics departments and you wonder about certain things. You've read about things. One of them, of course, is the unsolvability of the Quintic. And then you go through these courses and most of us don't see that proof. You may be an exception because you're an algebraist, but most of us don't see that proof in the course of our graduate studies. And there are various things. If you are slightly more physics-oriented, you've heard of the ergodic theorem, and it's a major backbone of statistical physics, of course. A lot of the historical formulation of statistical physics comes from the ergodic theorem, and vice versa. And yet again, many classes, we don't prove these things because the philosophy is, not in the technical sense, but the idea is that, oh, this is complicated. Just first do a year of algebra or Galois theory or in ergodic theory, first do a year of, I don't know, measure theory, and then we'll come back and talk about it. So I decided to try to break that barrier and write a book that is accessible for more people, and that's what I'm trying in this book. The third leg of the book is, besides the ergodic theorem and the unsolvability Quintic, is the prime number theorem, which we also give a proof of. Okay, and I'm going to do a little part of this book. The roots. So the story is this. The statement is this. We all know that if I say ax equals b, we can solve for x. We can also solve quadratic equations, x squared plus ax plus b, and so on. It's a small formula. But then you realize it gets harder. The cubic formula is about this size. You can write down the general solution for a cubic equation, and it's about this size. The formula for the quartic is from here to the wall of that house, approximately, if you write it out. It's very long, very, very long. That house, it's very long. You can find it on the web, but it's written so small you can't read it. You have to magnify, magnify, magnify. And then, of course, the end of the formula is way out of sight. The interesting part is that there it stops. You cannot do this for the Quintic. So the Quintic, not because you're not smart or because the people who looked at these things before you were not smart. No, because it cannot be done. By radicals. Yes, by radicals. Okay. Now, again, the traditional types of proofs involve Galois theory. I don't have an algebraic background, so for me that's very complicated. A lot of algebra is not so hard, but there is so much of it that if you're not an expert, it can be very confusing. And indeed, one of the common answers is, well, just study Galois theory, and we'll talk in a year, and then maybe we can give you the proof. And Arnold in '63, according to legend, taught this proof in front of high school students. Now, I don't think it was one session. It was probably a half year, and I don't know the real story. There's a book written on that proof by a person called Alexeyev. I forget where he is. He's maybe in Canada somewhere. But that book has 100 pages of, or a lot of pages of Riemann surfaces, which is also very complicated. And then other people deriving from going down the tree from Arnold to his students and ex-students and students of students have written other, including one in the Mathematical Monthly some years ago. It's a guy in Israel, Boas, a well-known physicist, has written about this as well. And so I took this, somebody in Holland wrote a thesis on this problem. And so I took all these sources and tried to distill a proof that I was happy with. Some of the proofs that I read, I wasn't happy with because I A, couldn't understand them, or B, they didn't seem to have all the details. And so I tried to get a complete proof. It wasn't easy, it took me a year. So I aim for understanding as the last little star. And not detailed proof. I understand this is not I gave this talk once before in front of a physics audience in Portland State. And you have to know in Portland State, the physicists are basically experimental climate type people. So they don't necessarily know all the math. So and the second footnote is to remind you, to tell you, so I may simplify, but I'll try not to lie. Okay. Oh. So this is Vladimir Arnold, and I thought it was a good statement. Mathematics is that part of physics where experiments are cheap. I like to add jokes. So this is part of my experience in looking up these proofs, that somewhere a miracle happens and you don't quite understand it. Okay, we're gonna do some language. Quintic polynomial, as you probably know, is a polynomial of size as indicated there that starts with a coefficient times z to the fifth. What I forgot to write here, C5, so the c's are the coefficients, z is the variable. The C5 is not 0, otherwise it's not a quintic, okay? The insolvability quintic, there's no finite formula involving the operations that I quote, plus product and their inverses, plus the radical, or there's the nth root operation that produces the roots of the general quintic polynomial, okay? I use the word insolvability. I think some people use the word unsolvability, but not insolubility, because in math we feel that that's for chemistry. I don't know why we feel that. Radical is an expression, as I said, the nth root of z, usually principal value, but not necessarily. Solution or root, it's a little bit confusing. A solution of pz equals 0, we also call a root in mathematics. That's very confusing. It's hard to write that because you have to be careful. The coefficients are those ci. Usually the c5, the highest c is going to be taken to be 1. Square roots, you could see the definition in the picture. Yes.
But what is the relation between the square root and the trees?
It's a joke.
This is the mystery.
No, that's a joke. I have not is the joke.
This is a square root.
And the square, okay, the square, oh my God. Okay. I'm very stupid. I'm very well known for not understanding jokes.
Now we have even more fun with the jokes. Thanks to you.
Okay, let's go.
Good. So I'm going to give you the outline of the proof, which I think this is only 3 slides. Which I think, because the details, there are some technicalities. But here's the outline of the proof. So on the one hand, I have the coefficient space, which are the C's. This is like, I'm taking as an example, say I have 4 C's. Remember, the leading C is going to be 1. So I'm thinking of a quartic polynomial. The quartic polynomial on the right-hand side over there has 4 roots, S1, S2, and so on and so forth. Now I'm going to do a thought experiment. I'm going to imagine paths through in C, but I parameterize them by parameter t from 0 to 1 that switches roots. Okay, but it achieves a permutation, so all roots are in the target space are targeted as well. And what happens, but the story there is, the trick there is that as I end this as I start the process, I have 4 roots. When I end the process, I have the same 4 roots as a set. As an ordered set, they're different, but as a set, I have the same 4 roots. What does that mean for the coefficients? Well, the coefficients do something entirely different. Because the coefficients depend on the sets, not on the order in which you give the solutions, but depend on the set of solutions. So the coefficients at t equals 0 are the same, exactly the same as the coefficients at t equals 1. So they're loops. Now, I can think of doing 2 things. I can think of, oh, I have the solutions. These solutions. Let's try to find the coefficients. Well, that's pretty easy. You just compute this. And so the product of all the S's is the last coefficient Z0 and so on and so forth. Very trivial.
That's Wiet's relations.
Yes. And so there it is. That's the C. Okay. Of course, what I aim to do is I want to go back. And that's the complication. And yes, if you have questions.
I have a question here.
Yes.
Maybe this is a detail, so maybe this is you will explain that later. But when you say that you permute the roots, you do it continuously. I guess that's what it is there. But then you do it through a path. Then I guess. And it doesn't matter which path you choose.
Yes, the reason I've made up 3D pictures is I don't want the paths to cross. And in 3D, you can easily see that that's entirely possible. That's not a problem.
Okay, okay.
And there, it doesn't matter.
Okay.
Does that answer your question?
Yes.
But it's not completely clear to me.
What is?
Of course, the solution from a set and the order of the set is totally irrelevant. What I call a solution 1 or 2 that change nothing. But when I permute, what do you mean by permute the coefficient? If I take the coefficient of the order of the 3 and you put in the place of the 4, it changes.
Take this C and if I swap these 2 C's, I get different solutions.
Of course, this is what I say.
But if I swap the solutions, the coefficients stay the same. That's the observation.
If I change the solution, the coefficients are the same.
Permute the
So if I
solution.
permute the solution, the coefficients are the same. But if I permute the coefficient, the solution are not the same.
Yes,
Okay.
that's it. Okay. So by construction, a general formula then that gives me the solutions from the coefficients should give all the solutions, because I can continue to permute until I go through all the solutions, all the different solutions. So for instance, if I want a general formula, then the formula that takes as input these four coefficients should give me S1 and S2. Okay. But I can also then permute S2 to S3. So then it should also give me S3, and so on and so forth. So that's one observation. And so here is an example. The radicals, here's the idea. The radicals in Q, so I have plus, minus, do nothing in particular. They're just bijections. But the radicals, they map a circle to a half circle, the square root, for example. The square root, if I take the square, here, I don't know, can you see this light point?
Yes.
If I take the square root of 1, I get 1. If I take the square root of I get a number here between 1 and I. If I take the square root of -1, I get I. If I keep going continuously along this path, taking square roots, I go from here to there. Okay. So what happens with these, this is a radical, this is an example of a radical, right? Square root. What happens with the square root, as it were, that's the, I'm sorry, I need the light. What I call informally, it needs to untangle this. It means to unknot this and put it there. That's how I get my solutions. Okay, now what's the miracle? Let's go back. So it needs to, my square root is going to untangle all of these guys and make them straight paths that do not close on themselves. Okay, now the miracle is this, that if I have 5 solutions, I can permute them in such a way that I can get arbitrarily complicated tangles. That if you give me k radicals, I cannot untangle it. I can always make a more, even no matter how big k is, I can always make it so tangled that you cannot undo it with k radicals. So there is no solution possible. Not with finitely many radicals. With infinitely many, yes. Newton's method, for example. Okay, so that's the short version of the proof. I have an illustration of this process. So take a simple polynomial, z2, z squared, plus 2 times e to the 2 pi it, which is this curve with radius square root of 2. Okay. That's C0. C1 is just 1. C1 is 0 because there's no 0 element here. And if you look at, so these are the C's, the coefficients. If you look at the solutions, they go from, S1 goes from I to minus I, and S2 goes from minus I to plus I. They permute. Okay. And so I cannot get, once again, I cannot get from the solutions C1, C0 to, the coefficient C1, C0 with a bijection. It's impossible. So that's why we need square roots in this case, or radicals in general. Okay? That's it. That's the outline of the proof. So if you got this, you got 60% of the talk.
But it's still very mysterious to me.
Uh-huh.
It's very mysterious. I mean, what does the tangling have to do with?
That's the technical part, yes.
Yeah, that's, I mean, one cannot fill in the gaps just by hearing this.
No, I didn't want to imply that. No,
this is still very complicated.
Yes, it's not so easy. But this is the basic idea. This is what it's grounded upon. This observation that you need to untangle this stuff, and that's not necessarily easy. I was hoping for a chemist in the audience. This is a chemical joke, because the department in Portland, the physics department, they have a chemical physics, chemical people with molecules, and so I gave this in our physics department. So I decided to add a chemical joke.
Of course, I do not understand the joke. It's not so important.
There'll be more jokes, don't worry. So I don't know how technical I should get, but we need to talk about groups, but I'll just do it. A group is a set of, and I'm not going to give long lists of definitions because I think that's pointless in a talk. A group is basically a set, a fixed set with a binary operation, so that if you take A times B, you get another element of the group. And every element, there's an identity and there's an inverse. And like the integers with plus is a good example. Now the integers with product is not a good example because there's no inverse. There's no inverse of 2 because, or let's say 3, because I can't go from 3 to 1 by using only integers. So I have to multiply by 1/3, which is not allowed. Okay. Another group is the group of permutations that I just talked about, which is called SN. Now it's called symmetric group. Symmetric, because if I permute the solutions of a polynomial, this is the historical reason why it's called a symmetric group. If I permute the n roots of a polynomial, the polynomial itself doesn't change. That's called a symmetry. And that's why these things are called symmetric groups. So SN, okay? And then we're going to look at commutators. Now, commutators are basically, if I do A, and this is multiplicative notation. So for those of you between 2 elements, I understand that is multiplication, whatever that means. You multiply A and B, and then you multiply by A inverse, and then by B inverse. Now, if the thing was commutative, the group that I'm talking about, then I can swap B and A inverse. And then, of course, A inverse is 1, or is the unit, and B inverse is also, so I get unit. So if I have a commutative group, this thing is just the identity. The commutator subgroup, so I can look at all these commutators if it's not a commutative group. So the commutator subgroup is another group. Let's not get into details here, but it's another group. And now I can do something else. I could say, oh, I can.
Sorry, if the group is abelian,
That's
commutator subgroup
the
is
same thing.
composed by the units,
Yes.
correct?
Yes.
Yes.
Okay, and so I understand.
Yes.
Yes, you do. It's okay, easier than the jokes.
Much easier for me. Mathematics is much easier than the joke for me. There is no comparison. The joke are impossible. Mathematics times I
I'll have a good
understand.
joke yet. Commutator subgroup. Now I can also look at, fly up and look at a distance at this group G. Did I start with, G, and subdivide it in these commutator subgroups and then translate, so to speak. So only look at the big units that are these, sort of translates of these commutator subgroups. And then I get another group. And I think you should realize by now, oh, that group is abelian or commutative because everything that doesn't commute, I took out. So the remainder, if I look up from 30 kilometers up, is going to be some smaller thing that is abelian. But the commutator subgroup itself is not abelian. So this all goes into these details that you asked about. Okay, that's what I said. I'm not going to prove stuff, I promise. Okay. Oh, definition. Now, definition. A group is simple if the only, now for technical reasons, we want subgroups that are a little better than just subgroups, and we call them normal subgroups. The only interesting subgroups are simple. A group is simple if the only interesting groups are the thing itself and E, which are always in the group, and there's nobody else. Okay. Solvable. Well, so if the group is commutative or abelian, which is the same thing, it's not a proposition, it's just different words for the same thing. Then it is solvable, but solvable is a generalization of abelian. If the group has a commutator subgroup G1, and G1 has a commutator subgroup G2, and up to a finite level, and GM is E, the identity. that we call solvable.
Okay. If there is a natural number. and
So
that-
for an abelian group, G1 is E. Okay. So this is a generalization of abelian. Why do we call it solvable? Well, you know the answer.
Yes.
I don't know.
Because those are the groups of permutations that we could solve the polynomial equations for, if the group is solvable. So there's a reason for that name. I always wondered as a student, why the hell do they call these groups solvable? Because you learn about them in, I was in physics, you learn about them in physics and solvable, but well, this is why it is.
So
What
to-
is solvable?
To every polynomial,
Yeah.
you can assign a group, which is
Yeah.
called the Galois group of the polynomial.
Yeah.
Okay. The polynomial is solvable if and only if the group is solvable.
That's why it's called solvable.
That's why this is called solvable. Because the
Okay.
you can
And
solve the
select-
polynomials by radicals.
And we'll see an example of that. in this.
A polynomial is solvable if you can
If you can find the roots
by
taking radicals.
by radicals.
Yes.
So
From
but,
the coefficients.
okay, but you can a polynomial of degree more than 4 can be solvable in
Yes.
some particular cases.
Yes, yes.
And the
Yeah.
group will be.
Yes. And so the 16th is 1. We can
Yes.
solve that.
Okay.
Yeah, so
Okay.
you will
So
have.
that's not yes, that depend on the degrees in the sense that for the degree 4 or smaller, all polynomials are solvable.
Yeah.
For the degree 5 or greater, some are solvable, some are not.
Yes, and the
There's-
Galois' contribution was to decide when.
Yeah, of course, clear.
And this is.
No, this is clear.
But this is a slightly different result what we're talking about here, because the result here is that for degree 5 and higher, there is no general solutions, that you can just stick in the coefficients, okay? Whereas for degree 4, there are general solutions. So there's a slightly different aspect from, it's not
That
that
can be said that
It's not the same as well.
polynomial of degree 4 is solvable.
Yeah, so it's not quite the same as the result in Galois theory.
Okay.
Okay, commutative subgroups are denominated with these funny square brackets, okay? Zn is the integers modulo n with the operation plus, is simple if and only if n is prime. There's no funny subgroups of, z modulo 5. So you might want to think about that. Any abelian group, I already said that, is examples of 1 is simple. So that's examples.
Sorry, remember the simple means?
Only to normal subgroups.
No, this I read. What is a normal subgroup?
A normal
By and large, it's a subgroup with an extra requirement. I don't want to get into technicality.
Yeah, so the thing is that you can make quotients, but by a subgroup, but only when the subgroup is normal. And that's the condition. It is, if you can make a quotient so that all the elements of your subgroup become 0, then in order to do that, you need your subgroup to be normal.
But what is the independent definition of normal?
Normality that for every element G of your group, G times the subgroup is equal to the subgroup times G.
Okay.
So you see a certain commutation there.
Okay. Okay.
So in particular for abelian groups, they're the same.
Yes.
So if you think of abelian groups, this doesn't come up ever. Okay. Now, what we're gonna prove, but maybe I shouldn't prove it, but what you can prove is that any abelian group is, an example of 2 is solvable. And the point of this talk is that S5 is not solvable. The reason for that is that if you take this subgroup of commutators, which is called the alternating group, there's also a reason for that, which is called A5 in letters, this commutator subgroup of that thing is itself. So you get the same thing back. So I can take commutators of commutators of commutators of commutators, it never ends. And this is where you get the infinite tangling eventually from. And so this group is perfect. That's that definition, if you're equal to your own commutator subgroup. Okay, so S5 is fundamentally different from S4 and below. Now, there's all kinds of notation for that. You call these things derived series. There's no need to go. Is this the next one? Yes. This is a nice picture. The way we analyze this, and this is standard algebra textbook material, the way we analyze this thing, that's the same picture, by the way, is you could write this thing as transposition. Transposition is just a flip of two elements, right? Here, 1 goes to 4, 2 goes to, and so on. How do you untangle this? Flip 2 and 3. Next, flip 2 and 4. Okay, that's this, 2 and 4. It's untangling from below, okay? So that's decomposing into transpositions. You see it happening? Flip to the bigger picture is easier to see. To untangle this, I flip this first, and then I flip green and blue, 2 and 4, and so on and so forth. If you have to do it by hand.
And the result, what is it?
And the result is that I can write this composition, this permutation as a product, as a composition. This is read, by the way, from right to the left.
I entangled
Of
2 and 3.
transposition, as a transposition, as a product of transpositions. Right? This means flip 2 and 3, flip 2 and 4, and so on and so forth. Okay, so this is the fundamental tool by which you prove this exercise that I'm going to talk about. Yes?
To entangle mean
Untangle,
untangle,
untangle.
meaning you find the unity. So,
Yes. You want to map.
and the only
You want to get this back to 1. And so one way of doing that is flip this first and flip that and so on and so forth. And this can express mathematically or algebraically as this. This is one way of proving. Usually textbooks are more implicit than that. I don't know how you teach this, but.
Yeah, so every permutation can be expressed as a composition of transposition.
this is a perfectly
Even
clear.
And
or
that's
odd.
this is what.
Yeah.
Even
And then
still.
you.
My problem is that unless I do not understand, when you are completely entangled,
Yes.
what you have is the unit permutation. 1,
Yes.
1, 2,
Yeah,
3,
yes.
Yes.
4.
Yes.
So, by
So that to entangle us is simply mean to find how many operations I need to apply to a permutation to find the unit.
Yes.
Okay.
Yeah, by the way, in English, entangle means to make it more complicated. Untangle means
Yeah, no, that
just
is
making sure that I'm understood.
Yep.
The only thing that you could check, which we're not in it, but you could check that there's a curious thing. The way you can untangle this in several ways, but there's also the parity is preserved. So here there's 5 of them. I can do it, I believe this is 7. I need to count. Yeah, this is 7. So I can also do it with 7 by just going back and forth. 9, 11, whatever. But I cannot do it as a product of an even number of transpositions. That's impossible. Okay. So we call these permutations, they're either even or odd. And now, then the theory proceeds in proving, and maybe I should leave this as an exercise. I don't want to go through all the details, but if you take Sn and you take the commutator subgroup of Sn, you get the alternating set, which is the even permutation. Remember, if I take what do you call them? A commutator, it's 4 things, so it's always even. So it's got to be a subset of the even. So it turns out you get all the even sets. That's called An, or the alternating group. Okay. But then it comes, this is the main proposition for this talk, or in the algebraic part of this talk, is then if you go and look at the subgroup that you got and you try to find a smaller subgroup, you can't do it. You cannot do it.
Remember the question of notation. Sn is the commutator of the cyclic group of
Yes.
n. And
Yes.
An, what
It's
is?
the even ones.
Yeah, alternating group.
The alternating group is the even ones
It's the
that are
even
a
permutation.
product of an even number of
Even
transpositions.
permutations.
It's half of Sn if you want to put it that way.
All the permutations that they compose as an even number of transpositions.
Transpositions, yes. So if I look from far away, I can look at Sn and I see 2 elements. I see this group An, which is one element of this smaller group consisting of bigger chunks, and An multiplied by 1 transposition. That's the rest of the group. Okay, so that's Z2. which is abelian, of course, because it's everything modulo the commutator.
So En is a subgroup of index two.
Yes.
Mhm.
Yes. Let me see. Now, the proof of this really isn't hard, but I don't want to make this an exercise in writing proofs. I'm happy to send this to you if you want. In my physics seminar in Portland, I had like 8 or 10 people asking for these notes. As you can see, it's 5 lines. But you know, you need to kind of point your finger at the right number and then look at this thing. I can do it if you want me to do it. Okay, the derived set. Now let's look at the other S's, S3. S3, you take so SA3 is the first commutator subgroup. You take the next commutator subgroup, you get the identity. So this thing is solvable. That says I'm solvable. Okay. A4, you get a famous group, the Viergruppe, which vier is 4 in German, which is spelled with a V. The first letter is a V, hence the name of the group, V. This has 4 elements. The commutator subgroup. You look again at its commutator subgroup, and then you get the identity. Okay, these are just calculations that you could do by hand. Once you know what you're doing, they're pretty straightforward. And so the derived series for these 4 groups, S2 goes to E, solvable. S3, first you get A3, then you get E, solvable, that's this. And then S4, you get A4, you get V, and then you get E. S5, you're out of, and higher, you're out of luck. You get Sn, you get An, and there the buck stops. That's it. It's given by God. There's nothing we can do about it.
So these are theorem about the symmetric groups.
Yes.
That as such has nothing to do with polynomials.
Correct, yes.
Yeah.
This is general
Simply
stuff that you
theory-
learn.
group
in an
theory
introduction
or
to
symmetric.
technology.
Discrete math.
Sorry?
It is discrete math. It
Yes,
is,
yes,
just
okay.
look at the
And
numbers.
insofar any group is a group of permutation, in fact, these are general theorem about.
Correct, Cayley, yes,
Because for Cayley, any group is a group, because you can
correct,
think any group as a group of permutations.
Yes.
And these are group of permutations, so
Right,
in fact,
correct.
these are property that apply to any group. Because you take a group, you transfer,
Correct.
Except
take
that-
a group of permutation.
There's only, there's only 3 that are solvable, so that doesn't apply to any group, right?
No.
The rest
So-
is not.
No, what Marco wanted to say is that you can embed any finite group in one of these
Finite
people.
group is
So,
a subgroup of the group of permutation.
yes,
Not is the
not
group of-
itself, yes.
Is a subgroup of.
So I cannot transform any group in a group of permutation?
The order of the group of permutation is factorial n.
And factorial.
Okay.
If you take any group, it doesn't have.
Okay, so when I transform a group in a group of permutation, I change the order. That's the point.
No, it will be a group, but not the total group of
Exactly.
permutations.
Of.
It will be some permutations.
Exactly. Yes.
Let alone infinite groups. of
And
course.
then there are certain theorems that will relate, for example, every subgroup of a solvable group will be solvable. But these theorems are not telling much because when you see, if you have a group with more than 4 elements, this will be a subgroup of an Sn with more than 4 elements.
what
And then
n
you
is.
do not know anything about that group. So
You don't even know
So
n
see-
necessarily.
those theorems are very limited to symmetric groups.
This is typically, I don't know, senior level, junior level algebra, right?
Yeah.
Okay. The word soluble, apparently a linguistic comment is never, people call them solvable, not soluble, and I don't really know the reason for that. Now, here's the thing that you could do. You could then assign a commutator depth in Sn, in these groups, of an element. So you take an element of that group, and you indicate the size of the maximal nest of commutators that yields that element. Now, I have wonderful chalk here. You guys have the highest quality chalk. So here is an example. This is a level 1. Okay, this is a level 2. Gamma, delta, and it goes up, you know, the writing becomes, alpha. Oh my God. I'm getting confused. And it doesn't fit anyway. Formula gets to be too long.
At each step you add just one element.
Yeah, but so this thing is 2 to the n long for if it's depth n. Right, so so the question, but there's a maximum size that you can assign to it, and that's what we call the depth of the commutator. Okay, this is not in your algebra books. Examples. Oh, here is an example. The depth of 1, 2 in S2 equals 0 because it is not a commutator, and you cannot write it as a commutator. Because why? For example, because it's a transposition. It has one transposition in it. So it cannot be written as a commutator. So everything that is odd, that has odd parity, cannot be written as a commutator, and it has a depth 0. Okay, a single commutator has depth 1. Let's see. The elements V in S4, here is S4, the elements of V in V, where is V? Oh, there it is. The depth equals 2, and so forth. Any element in AN for n greater than or equal to 5 has depth infinity, because I can keep writing it as a bigger and bigger commutator. I get the same element, because if I take all the commutators in A5, I get all of A5 back. So I can always write an element that I have as another level of commutators. I can keep going down. So the depth is infinity. Okay. The depth of the identity is also infinity, by the way, because the identity, obviously, E times E minus 1 times E, it's E again. So I can keep going.
I have an historical question.
Ah.
So if you look at it and you do not know that there is a Peter here that is given a talk about the Ruffini-Abel question. So you see that, you know the Ruffini-Abel for another source, and immediately you see there is an analogy here because there is something, this block at 5. So you know, here, I am not speaking of polynomial of solution, I'm speaking simply of the metric group. And I see that 5 is a limit. Then I remember that 5 and there. So the two things were discovered completely independently.
Which two
Or
things?
originally the two things had a connection. So this appeared when Galois.
No.
They didn't know
Ruffini was
anything
much before.
Sorry?
I mean, the
figure-
concept of group didn't exist. The concept of group was not invented yet. The concept of group was invented to formalize the whole theory.
The theory of group was invented, yes, by Galois to formalize that.
Highly.
Yes, Kelly, but
That's
yes,
the
yes,
1850s, right? I think.
Yeah, much later. So, I mean, of course, they had some notions of there's something going on with permutations, but to say that they have these results, and this result was
yes. I want to say when Galois worked to the question of solution, introduced the notion of group, not exactly, but introduced the prehistory of the notion of group, but used this result is this result used by Galois?
No, he didn't use this result, but
okay. So then when you have the notion of group, you can find that this result independently of the solution of the polynomial.
So I think in current mathematical language, that would be very hard.
So
I think this is a step you need to do.
So Abel and Ruffini, they knew that these permutations are related to the solvability, and they were looking for the solvability.
Yes.
Yeah, they were looking for the solvability of
the two things are entangled from the very beginning.
From the beginning, yes.
So my guess is
beginning to think are entangled.
My guess is that
this is the question.
Implicitly, Ruffini somehow saw this. Is my guess.
Okay.
By the way, if you're interested in that, I know that Daniele has a book that has the theory that Galois wrote on his last days. But he hasn't read it, but he says, I can dig it up. So if you're interested in history, Daniele has the book.
Okay, no, that I know. Okay.
Oh, okay. There we go. So an extra result that might be interesting if you look at the actual solutions later is that, you know, that if I divide out these commutator groups, I get abelian groups. So here you see Z2, and then I get Z2. And for the cubic, the S3, I get first Z2 and then Z3. For the quartic, I get Z2, Z3, and then Z2 cross Z2. And of course, for greater than 4, I get nothing. I get Z2, but then nothing. And that is reflected, although I don't quite understand how, but you look at the general solutions for 2, 3, and 4, and well, 2, you have Z2 in it. For Z, maybe you guys know this, but for the cubic and quartic, you could see it, but to make it explicit is a little hard. All right. Loop space, this is a restaurant somewhere. I couldn't find it.
the with the index is the group, the symmetric group on the integers.
The cyclic group of the integers, yeah.
Wait, sorry, I didn't understand the question.
So what is the difference between S2 and Z2?
Z2 are numbers.
S2 is the what do you call them? The permutations. S3, Sn are the permutations on n integers.
Yeah.
Zn is the cyclic group. So it's Z modulo n,
Yeah, exactly.
but they're not the same.
Yeah, no, of course, it's not.
Okay.
Of course.
Okay, there's apparently a restaurant that has loops in it called Space Loop.
Of course, I do not understand that.
It's not a joke. No need to understand. Oops. Okay, so now we're going to look at the topological part. We're going to look at loops. And so we can define something like a winding number. Now, here is the 0 of my coordinate system. This is the complex plane again. Here's 1. So I have various loops based at 1. And I'm going to tell you, I want the number of times it winds. The loops cannot cross 0. Okay, and now I want to know the number of times it goes around 0. So the blue loop goes around 0 once, and we say it has winding number 1. The green loop, if you look carefully, I think it goes this way. It goes around the origin -2 times because it goes in the wrong direction or in the clockwise direction. And so we call that winding number 2. This one, don't make no mistakes, this has winding number 0 because it doesn't go around the origin at all. Okay?
The green one goes around the 0.
It has winding number -2 because it goes in clockwise direction. In mathematics, anti-clockwise is positive. I don't know why. I said that already. And we say that now this group, we call it homotopic, but the groups, the loops can be deformed if and only if they have the same winding. These are continuous paths, okay? If and only if they have the same winding number. That's another result. And we call those equivalent or homotopic. Okay. Oops. Now, come on. Okay. Now we can make groups of loops. And we could by concatenation. So the operation that we could do is concatenate. Here are 2 loops. They go from they're parameterized by a parameter from 0 to 1. I can squish them a little bit so that they now live in 0.5 and half 1. And they have to have the same endpoints. Okay. And I can glue them together. And we call that concatenation. The winding number, you will not be surprised to see, is of course the sum of the winding numbers of these guys. Okay. So and then I get the inverse of its winding number. So these things form again an additive group. Okay. In the group, the inverse in that group, the inverse of this is of course the winding number of some other loop, but its winding number is just minus that winding number. I mean, I'm stating the obvious here, I think. Right? It is what you think it is. Now, if you study algebraic topology, you can spend months on this, but we're not going to do that. So I get another group with addition. Now I need to. Oh, here. And so now I'm going to lift the loops. Now, what we mean by lift the loops, that's a word we use. Let's start from the other end. Let's say I have this picture and I have a polynomial map. Polynomial maps are very easy. You just apply the polynomial, you get something else. But the problem is if I want to lift it back up, if I want to go the other direction, the polynomial may be a square. So if I want to go back, I get a square root. And so everybody has 2 pre-images. So this thing here has 2 pre-images. Now the way you lift the loop is, but look, remember the 2 pre-images are kind of far apart. So the way I lift consistently and talk about topology and get continuous stuff is by saying, okay, wait a second, I'm going to look at a teeny area here, and then I'm going to lift that. I still get 2, but now I'm going to choose 1. Okay, and let's say I choose this one. Okay, and then I say, okay, now I can, in this little neighborhood, I can now take the inverse image, and I know where it is because it must lie in here. And now I could take, and now I say I end up at this point over here, or this point over here, and now I can keep doing that, taking little neighborhoods, and then by continuity, I get a unique curve. That's how I lift loops. So I could take an image of a continuous curve. So I can take a continuous curve, and I take an image. I can consistently take an image under a square root and get one continuous curve. That's how we formulate it in mathematics. So that's what this says. I don't remember how I stated. It's a while since I gave the talk. Okay. Now monodromy is the winding number. The winding number of this loop induces a permutation on the point. So here I have only 2 points that are inverse images. But if I had 4 points that are inverse images, if I take a curve that goes around once around the circle, okay, then and I have four pre-images, one here, one here, one here, one here. Oh, they're named. 1i minus 1 minus I. And if I take this loop and I go around the loop, what happens is here I go from 1 to I. Or if I start at I go from I to minus 1. So if I number these things by 1, 2, 3, 4, I get this permutation. Okay. Now, of course, if I take a loop with winding number 2, I go from 1 to minus 1. So I get this permutation. I go from 1 to 3 and 2 to 4. Okay, and so on and so forth. So that's the winding. That's called monodromy. The commutator of 2 loops, A and B with the same base point, is given by this. I already said that, I think. In the loop space, I can also declare a commutator depth. The way, suppose you take a circle, let's just take this circle that I call alpha here. I know it's not a commutator because if it was a commutator, I have to pass through each point at least twice, namely once in one direction, and later on I go back. So I know if I just take this black loop, it's not a commutator. I know its endpoints are the same, so it's a loop of depth 1. Okay. In general, I can, yes?
Depth. You said that it's
The
not
maximal.
yeah, but you said it's not a commutator. So it's depth 0.
I think I call a loop as depth 1. Maybe you're right, depth 0.
I'm not sure, but
No, I think you're right, depth 0, sorry. Yes, the depth. Oh, here is my formula. So I can, the constant loop, right here, constant loop is something, for example, that stays in 1. My endpoints are always based on 1. I need to, and you can see, I can write that as a commutator of a commutator. There it is. Here's another commutator of a commutator. This is depth 2. Okay. Now I know that I pass each of these points. Well, it gets the computation gets a little harder. Now you can't, you try to draw this thing and it's impossible to make sense of. It's a very complicated thing. That's one of the reasons we cannot intuitively easily understand this, I think. Each simple closed loop, this is depth 2, is traversed 2 to the 2 times, half of them in each direction. So I can assign this depth. Okay, it's a non-trivial statement, but I can consistently assign depth to these loops. That's a joke.
That I understand.
Unsolvability, as opposed to this, with trying gentler methods.
I want only to understand who is the person that has died in your talk. You kill who are you killing now?
Okay, now here's a lemma. Here's a lemma. If alpha is a loop, then it is possible that the lift of, we saw that, right? You take the square root of a loop I get something that is not closed. So that proves the lemma. If alpha and beta are loops, then the commutator is a loop. Okay. And the reason is so simple is because if I look at the winding numbers of this thing, alpha, beta, the winding numbers, they're just additive, right? So it's the winding number of alpha is A, the winding number of this other guy is B, so A plus B minus A minus B is 0. If I lift something with winding number 0, that is a loop, it stays a loop because I don't go through the origin. All right? That's all you need to prove this lemma. Okay? The proposition then is, if I have a path of depth k that I defined before, then I keep pressing the wrong buttons. If I have a path of depth k, then if I take a radical, I get a loop of at least depth k minus 1. And now you begin maybe to see how the proof is going to go. The proof is of this proposition is pretty easy. It's basically this lemma plus a trivial, I need to modify that, what do you call it, induction argument. Now, in my view, most induction arguments, you give an induction argument if you don't really intuitively understand what's going on. And that's with this. It's hard to visualize this. I can't visualize this and I've tried very hard. And so you give this induction argument, which is childlike. It's like the arguments for cowards. I can't put a picture to it. But it's only 2 lines. Anyway, let's not get into the details. You just use the lemma and then, and then use a standard induction argument, which is in some sense not comprehensible. But so here's an example. Let's suppose I start with this loop and I take the radical. Here's 0. Okay. So what happens? So I go around once. Remember, I go around once. Let's say it's a square root. So I go, this is not a closed path. Okay. Then I get this loop 2. There it is, 2. Now I go back 3. Well, it's the same path, but backwards. So I have to go this way. Now I get the loop 4. This is a loop, but it's not a commutator.
Loop?
It's a loop. Loop is a closed path.
Yeah.
But it's not a commutator.
Nice.
Because I pass through these points only once. So it can't be a commutator. So I decreased the depth. Okay, that's an illustration of that lemma. And then you could do it otherwise, and then you could let loose another radical, and then you get a path. Sorry, a non-closed path. Okay. So now we have all the ingredients, I believe. So the insolvability of the quintic, there's the statement again. So these simple operations plus radicals, finitely many of them, I cannot give a general solution that applies to all quintics or higher order. Okay. Again, the difference with Galois theory, Galois theory in one sense is stronger because it tells you which polynomials you might still be able to solve. This theory does not address that question. On the other hand, as I think you remarked this afternoon, we really rely mostly on topological arguments, and that the operation is plus or minus. It doesn't really matter. It might be other. You might be able to use other functions. So in that sense, it's a little more general. So now we get the question of relating this to the actual formulas. Topological nested radicals are expressions of the following form. You have to read this as D1 times, that's multiplicative here, the m1th root of some other expression E1. These are expressions, and the expressions are combinations of the coefficients with these guys. Okay. So this is a nested radical of depth 2.
So what are D and E?
Expressions.
Whatever.
No, let's keep it simple. Expressions that combine coefficients and these signs, but not the radicals.
It is not radical.
It's kind of hard to point at only these are not the radicals. So
They are rational expression.
yes. Yes. You have to be careful with division. Division is not always allowed, but never mind. And the reason is if you divide by a coefficient and you set that coefficient 0, you're in trouble.
But they are,
That doesn't
they
matter.
are expression in which variable?
C's.
In the
Yes, the
coefficient.
C's, yes. Okay. Here we go. So theorem. Here's the same pictures I showed you before. Let K be the maximal commutator depth of non-trivial elements of Sn. Right? You don't want to exclude the identity, which is always depth infinity. Then a general solution for the degree n polynomial must contain topological nested radicals of depth at least K plus 1. Why? Because I need to go, if I have a depth of nest K, I need to untangle that because I need to get these permutations. I need to be able to do permutations. These permutations, they end up, they're not closed loops. So they after I have depth 0, I need to go one more step. I call that depth minus 1 because they're not closed. Okay, that's how I get the plus 1. Now the proof is basically what I've said before. Take a sigma, a permutation of depth K here, whose constituent permutations are depth 0. Okay. Then each of these occurs 2 to the K times in sigma, and 2 to the K minus 1, and their inverses do too. Then each constituent permutation is induced by a collection of paths in here, right? I can make those permutations happen by cooking up these paths over here. Okay, and then I can find the coefficients. Right? So then I go do the coefficient, I get myself a permutation, I realize it here, then I compute the coefficients. Then you can easily see that these are now loops in parameter space, but they have the same depth because if I use this permutation here once, K times, then I also see the same element back K times in this expression here. Right? Because it's the same thing. So the depth is the same. And so that gives rise to a commutator here of depth at least K in the coefficient space. Q needs to map these depth K paths back here to paths that aren't even closed. So they have depth minus 1, as it were. Now, by the previous, I need K plus 1 radicals at least. Okay. Now, remember that for degree 5 and higher, this K, permutation depth K, can be arbitrary. So I can never do this with finitely many radicals, and that's the proof. Oh, that's what that says. Okay. So this is another, see the quadratic, as I pointed out.
Sorry. Can you come back?
Yes, of course.
It's not so clear to me why this corollary is immediate.
By the corollary is
The
true?
Cavern-Neston radical cannot entangle a path of depth K1.
Yes,
Why?
because the proposition that I just showed you said any solution, any
Yeah.
kind of,
Yeah.
I need a radical.
No, this I understand, but why it cannot be if in the case of 5?
Because at 5, you can get arbitrary depth. I can get you remember A5 is perfect. So that means I can write elements A5.
Because of the proofs that we made before about
Yes,
the group.
yes.
Okay, so it is okay.
Yes,
okay.
exactly.
Because at 5, you do not find a solvable group.
I can, so any element of A5,
The chain.
I
is
can write
infinite.
as, say, a depth 20,000 commutator.
Okay.
So I need at least 20,000 radicals, but then I can write it as level 40,000, and now I need 4, and so it can't be done. Okay. Cubic and quartic equations can be solved, but I should say that by and large, we never, well, quadratic equations are common, but the cubic and quadratic equation we essentially never use in math because it's just too complicated. And you can see the guy. In my view, what I tell my students is that, in my view, so this is, by the way, this is a truly nonlinear expression.
These are things that one learn at high school and then take for granted and then never look at the details. If I remember well, the case of Quintic is simply the same of the case of third degree because we reduce an equation of 4 degree to an equation of third degree.
Yes, but the reducing takes effort, and you know, if you write the complete formula, it's more.
Okay, so here you write all the okay. So you compose the two operations.
You can't
Then
write
find the root of a third degree equation composed with the reduction. Okay.
That's a little more complicated.
Okay. No, I tell it because this is a formula that of course I know. This is a formula that I know. I never said that, but I never said that because anytime that the Quintic, you think you go to this and then you look at this. Okay. Now I understand.
So this is the steps. If you want to go through it, these are the steps. But you know, and then you go through these steps, and now I give you an actual quadratic equation, and you try to solve it. You'll be surprised how non-trivial that is. Okay, I have a couple of exercises in my book, and it took me half a day to do one of these exercises. A radical ending. I don't know if you like fairy tales.
This is a joke.
Yes.
It's a radical joke.
Explain me, please.
So the princess is in the tower and she never got rescued because the other two guys decided to
They live
get
together.
Okay.
A radical ending.
Okay. So definitely mathematics is much simpler than thought.
So here's the structure of the solutions. You can see that I just showed you the quadratic solution, and that has Z2 in it. That's pretty clear. Remember that I showed you this, as I can talk about it. And is 3 is something like this, is a third root of quadratic solution, and that has that has Z3 in it because of this. And 4, that's this guy, it has 2 groups in it, and it looks somewhat like this. It's not the same as the cubic. But although you use the cubic to solve it, it's not the same. And you get something like this. So it has these 2 things in it. Okay. But I can't, can you translate that exactly? I don't know if that's known even. Maybe in Galois. If you know this, my instinct says you should be able to predict the general form of these things.
Yes, but by looking at the solution at the series,
And so
the
it gives
composition
a
series.
hint that.
Yeah.
Not worked out. Okay, that's it.
Now, can I make the two questions? First
Of
one,
course.
the story that Arnold were giving is proved in front of 2 high school. I see only 4 possibilities. Either is wrong, it's not true. 2 possibility, the story is not true. Second possibility, you are a very good teacher. I think that your pedagogy is fantastic, but the actual solution, Arnold pedagogy was even much better than yours.
Well, he took half a year, I think. It was not one lecture.
Okay.
A lecture series.
The high school students, they were really very good high school students.
Best high school in Moscow State.
No, three
Moscow,
possibilities.
Moscow probably.
That's
None of it was true.
Either very good high school teachers.
But it was not one lecture, okay? It was like a whole series.
No, okay, but now the serious. So sometimes I make jokes also.
Oh,
The serious question.
yeah.
How much is this proof different from Galois?
Oof. So the
No, because I do not know in detail. I don't remember exactly in details Galois proof. But
so the starting.
intuitively speaking, I have the impression that in the end of the story, it is a simplification of Galois proof. Am I wrong? There is an essential difference between the two.
So the Galois proof starts also with the S1, 2, 3, that S5 is not solved.
Yeah.
Okay. But then this proof really is different because you don't need to stick to just multiplication and division. Galois proof uses strictly algebraic techniques. They rely on the fact that the what do you call them? The complex numbers form a field. And so you can only use plus, minus, multiply, division.
Mhm.
This group, after you establish the necessary, this reasoning, after you establish the necessary details about your groups, A5 in particular, you then turn to topology. So I could use more general expressions. But this theory also does not explain, on the other hand, does not explain what individual polynomials, as Jose pointed out, the Galois theory says something also about individual polynomials. This theory doesn't care about that.
No, that's a lot.
So okay. This theory only tells you there is no general solution for 5 and greater, okay? Galois theory goes a little further in one sense, because it says, okay, but certain polynomials you still can solve. There's no hint of that. The other difference, that's one difference. The other difference is that here I rely on topological arguments for the second part of the proof, which Galois theory does not.
Yes, that is clear.
And so
Yes.
there's a consequence to that, that in Galois theory, you can only use the operations plus, minus, the field operations. Here, I could do without. I can make a
Okay,
more general
now,
statement.
okay.
So it is slightly different.
Okay, so let me tell the question another way, in another way.
Mhm.
You take Galois proofs,
Mhm.
and then when you arrive to a step in which you need to work on the general property of a field, instead of looking at this level of abstractness, you go topology and you reason topologically. So in some sense, you repeat Galois proof by using topology to simplify a part of the proof, or not.
I'll be honest with you, I don't know the Galois theory proof because it's very complicated. It's hard to summarize that.
I also don't.
So I don't know. Maybe Jose knows, I don't know, or maybe you know.
So because intuitively speaking, Ahmed probably has a better know the thing. Intuitively speaking, it seemed to me that the basic idea is the same. This is possibly not.
No, it's not.
So
No.
No, it's not, and I can tell you why not. Was my trying to say. The algebraic proof works for any algebraically closed field. Those algebraically closed fields may have a zero topology that you can do anything with. So they're more general actually than this proof, right? Because this proof is tailored to the complex numbers.
Yes.
Where you have this,
yes.
all the continuity and so on, there's no continuity.
On the other hand, since this proof relies on continuity, these proofs can be extended to say that the polynomials with degree 5 cannot be solved by radicals, but they cannot be solved either by other continuous functions that behave like radical.
Okay, so it has this.
So they
more
really-
general.
Yes.
In one sense, it's more restrictive, but in another, more general.
Yes.
So the two sets with an intersection,
Huh?
but the set difference, they both have things that are not in the other set.
So suppose instead of radicals, that somebody imagined another function
For
of
example,
complex,
cosines. Can we solve it with cosine?
whatever. Yeah, ease, that kind of thing,
Yeah.
right?
Yes.
Ah,
Yeah.
so it's much more general, actually.
No, it depends.
In
on
that sense,
In that
in
sense,
that sense.
So what is why is
Because it allows
I got the
all
wrong meaning.
kinds of
Why is my general?
it allows all kind of analytic functions, for example, over
Or even
complex
continuous.
numbers, or even continuous.
Yeah.
I mean, it says basically that they're as unsolvable as it gets. It's
So
not
you
just-
mean that with this proof,
Sorry,
you are
what-
proving
what
that
is outside Galois.
Exactly. Yeah.
no,
Exactly. So-
let me understand.
So-
I
what
am
you're saying.
sure that
So,
statement is
Well,
correct.
what Marco is saying is how does this proof compare with the Galois proof?
Yes.
Yeah.
And the answer is it's very different because this proof relies on continuity
I don't
and
know
not
your name.
assent.
Can you say, what's your name, sorry?
Ahmed,
Ahmed, Ahmed wanted to say, you've been raising your hand for a
Yeah.
while.
I have just two comments to say here. There is Abel proof, and when Abel gave his proof, Galois was 12
Yeah.
years old. So the proof of Abel is completely different from Galois. And I know this proof of Arnold.
Oh, you do?
He called it the dance of roots, the dance of the roots.
Oh,
And
we have to
this-
talk, because I'd like to.
And this proof of Arnold is almost similar to the proof of Abel, because Abel used Abelian function, Abelian integrals. So, and in the Abelian integrals, you have the problem of analytic continuation. So you have the problem of the monotropy groups, and you have all those things. But what the comment that I wanted to say is that when we take Quintic, it has 6 coefficients, and we can assume that the leading coefficient is 1.
Yeah.
And we can, by translation, heal
So now you have 5.
the fourth order, the degree 4 terms. So we have 4 coefficients. Fundamentally, we have 4 coefficients. There is a method of Brioski who reduce the solvability of the Quintic to another Quintic depending only on 1 coefficient.
Is that the Bring radical? There's something
No,
called the
not
Bring.
Coefficient, what does-
Yeah, 1. Only all the
And
coefficients
the other coefficient are function of 1.
of 1b. Yeah.
The others are constants or what?
No,
The
zero.
coefficients are coefficients, but they are expression of 1 parameter.
Ah,
One parameter.
B shows up in many versions in the other coefficients.
Yeah,
Oh, okay.
and that's b. The point is that here you used the alternate group A5.
But if you do that, so now the space of solution is based by only 1 object.
No.
If you say,
The problem is
Yeah,
that
but
to express this b, and this b, to find this b, I call it b because it is Brioski who did that. And this b depends fundamentally on the alternate group A5.
On the what?
The A5,
Oh, yeah.
which is of order 60.
Yes.
So now here we have the geometry of the icosahedron. The isomorphism group of the icosahedron is exactly A5.
Yes.
And then you have Quintic of degree 5, A5, and you have the golden number, which depends on root of 5. And you have many 5s. So the geometry of the Quintic depends on the icosahedron geometry and the duality between the icosahedron and the octahedron. And the dance of the roots of Arnold can be seen on the dance when you take the icosahedron and you project it on the plane by stereographic projection. You have some vertices, and the dance of the roots are exactly the dance of the vertices on the plane.
Wasn't this the subject of a book by Felix Klein about this?
No, this is more recent. Because to find now,
more recent.
to find the roots, the B of Brioski, to find the B, because the roots depend on this B. We have some very remarkable continuous fraction of Ramanujan. And that Ramanujan, the power 5 of this continuous fraction are remarkable. So this 5 appears in many places in pure mathematics, in mathematics. So
is that related to the only one I know is that you could solve the Quintic in terms of the Bring radical.
yes,
This is another Quintic.
yeah, but here you have you have less coefficient. You have to reduce to 3 coefficients.
I don't remember.
And maybe in
It's in this book that I
transforming
wrote, but I don't remember. I didn't.
so you have a polynomial of degree 5.
Yes.
You take it monic, so you
Are
have
we still doing?
5 coefficients.
Yeah, you kill by translation. you
One,
have
so you have
like
4.
4
So
coefficients.
4 is, and then for
Ask
4
if
to
the
1.
people in the audience that are
No,
listening.
not to 1, not reduced to 1.
I want to give a moment for the people that were online to see if they have questions.
yes.
Can you ask? Okay, so there is only one person in line online. I don't know if you have any question. I think we might be able to hear you. But they might not have any question then.
Okay.
Or we might not hear them.
Maybe they cannot hear us.
Nobody knows.
So you take to 4, but that function of.
No, that's 4. You can find another Quintic.
Yeah.
This Quintic will have 4 coefficients,
Yeah.
and those coefficients are function of 1 parameter B.
And the two quintic are the two polynomials are symmetric. How they are connected?
Yeah, you can, if you have the solution here, you have the solution here.
The solution of one and solution of the other. So from the solution one, you got the solution of the other. So you already, okay. So after all that, can you answer again to the question, what is the fundamental difference between this proof and the proof of Galois?
The methods are very different. So this method relies on topology and on continuity. So
No, this is a part of the proof rely on topology.
yes,
The proof itself does not rely on topology. Topology is used for a lemma of the proof, if I understand.
and then topology relies on the proof relies on topology in the sense that it relies on a lemma that relies on.
Yeah, that's
So
okay.
in other words,
That I understand. But I want to say the structure of the proof does not rely on topology.
No, that's
Topology
fine. No,
is
no, no.
useful to
Yeah.
prove a piece of the
no,
Exactly.
the notion of continuity is absolutely essential. You cannot write this proof without having continuity at your disposal. Not possible.
Okay, monodromy.
No, I
So
understand.
just the
my
the
point is
idea
that
of entanglement.
I have an architecture of the
Yes. Yeah.
Okay.
Exactly.
And then when you have an architecture of the proof, you have a cathedral, you have to construct the different column of the cathedral. Okay. So to construct a cathedral, a column, you need wood. To construct another, you need marble, etc. So the fact that you need wood for a column does not mean that the proof is a proof based on wood, the structure of the proof. So the idea here seems to me that topology enters to construct a column, not to identify
This
the
is
structure
subjective.
of the proof.
But
Or not.
There's a question from the back.
No, I think that the point is that, I mean, with this proof, you cannot make this proof without the notion of continuity.
That's I
That's
totally
important.
agree. That's
So
I
maybe
totally agree.
Let's go back to your thing with the cathedral. So yeah, maybe you have this column, but the thing is, you cannot think this column without the notion of continuity. And if you don't have this column, you don't have the cathedral. That's the point.
That I understand. So my
And
question is,
Galois didn't use
can
the
you-
notion of continuity.
you take the wood, you put in the rubbish, and you use the cathedral go back. But
Yes.
before that come back, you take stones and you put the stone in the place of the column. Can you do that? So
No.
can you replace
No.
topology
it
with
will be-
something else? This is the
No,
question.
it will be a different proof.
You will be completely different.
Because the main idea of these proofs is to use topology and continuity, monodromy, and
Yeah,
those are the main tools.
Okay.
The main
Oh,
substance.
This is the second part at any rate. The first part is
That's
the
the
same.
question. So
Yeah, and
topology
therefore-
does not enter here as a local tool, but is part of the
Yes.
global
Yeah.
understanding of the.
So I want to
And
remind you that this is a subjective statement that you make,
Yeah.
okay?
Yeah.
But I agree with what he said.
Yeah.
It is a subjective statement.
And because of that, you have two main differences with respect to Galois proof.
Yeah.
Because the Galois proof doesn't use these terms. One is that it is limited to the complex numbers, while Galois proof can be proven by fields of many other characteristics. And
Yeah, okay.
okay. On the other hand,
And this makes this proof more particular
yes,
than the Galois.
exactly.
But there is another sense in which it's more general. So what
Exactly.
is this other
The other
sense?
sense is that here it is the radical and the addition and multiplication, and those are the continuous functions that you're using, but you are not limited to those.
No.
You could use other functions. So this proof is going to tell you that you cannot solve the quintic not only by radicals,
With continuous function.
but with many
Exactly.
other kind of continuous functions.
Okay.
Yeah. So it is.
Not even if you put exponentials and logarithms and sine and whatever.
So it's less general because it's concerned only equation on a C and non-equation on whatever field.
Yeah.
Yeah.
But it's more general because
Yes.
say that there are no continuous function
Yes.
of the coefficient that give the solution.
That is going to give you.
Which makes
Continuous in general or a family of continuous?
continuous, yes.
So this has been remarked in the literature. I don't know if anybody has really gone in depth to see what exactly you could use and not
Yeah.
use. I've thought about it, but I decided
So
not to include
the
it.
question then is the following.
Yeah.
Can we resume this, the theorem that we are proved, you are proved here by saying that there is no a solution of a polynomial of 5 degrees by continuous functions.
But you'd have to.
Or continuous is too much.
I'm
This is the-
I'm skeptical.
You have to be very
Sorry, I
careful.
think this is too
I'm
much.
not, I don't agree with this kind of, because continuity is outside. If you take some from no algebraic function, this is outside algebra, outside the Galois theory.
But
outside
then the
everything.
second point.
Isn't this
We have to make
a
things
bit connected
visualize.
to Hilbert's seventh
I'm not-
problem?
I'm not.
I don't know.
So,
Because it
What's the
seems
what-
like you have a
what-
function, you see, Hilbert's seventh problem asks for, if you have a function of many variables, can it be written in terms of functions of fewer variables? And here, you can think of the solution of the quintic is a function of the coefficients. And you're saying, well, it can't be written as a composition of those. So you have to be somewhat restrictive. You have to stick
Yes.
with the plus and times and so.
I'll give you.
Because else the solution is positive. Again, Arnold, right? Arnold solved it for continuous functions. For functions in general, it's still unsolved.
Well,
Hilbert's seventh problem, right?
function
for function in general, no, function in it is. No,
Let me give you an
because-
example of a restriction. That's very simple.
Yeah,
Like I said, oh, it's gone now, but I said plus, minus, multiply, divide. For instance,
Yes.
you can't use divide.
I understand, yes.
Because if I divide by a coefficient, I make that coefficient 0, my solution goes to infinity. And we
Yes.
know that that's not gonna happen.
Yes.
And so you have to be very careful. So I don't know, continuous functions, what do I mean multiply C1 by C2? How does that a continuous
Yeah,
function?
there is a tiny restriction there.
Do they have to be invertible? So you have to be more careful. with that.
Yes, yes, yes.
But I don't think it's
Continuous
continuous if
is too
anybody's
much.
interested.
But clearly, it's much more general than just
Daniela
the
wants to write
algebra.
a paper in the monthly. So if the 4 of us figure, the 5 or whatever of us figure this out, we can all write a paper in the monthly. I don't think it's figured out, but I could be
No.
wrong. I'm not a specialist.
But you're gonna publish this, right?
No, yeah, but as a textbook.
In the textbook, it's all in there.
Yeah, did what I said and some more. There's also you mentioned this other thing. The only thing that I knew about that is you could formulate the solutions of the quintic in terms of the Bring radical, B-R-I-N-G.
Uh,
And that's another quintic polynomial, and you can, but apparently it's not easy to do that. But so I give an example in the book, but I don't go in depth. You can also express the solution of the quintic as an infinite number of radicals. That's like Newton's method will do that, I believe, if I'm not mistaken. And so on and so forth. So there's all kinds of ways around this.
The Bring equation is x5 minus x plus constant.
Yes,
You have-
I don't remember
You have
exactly.
many gaps in the equation.
Yes, it is a quintic. And so you can express the solution of the general quintic in terms of this radical. And it has a shape like this. I have a picture in my book. So something like this. And as you move A, as you add A, the solution goes from minus infinity to plus infinity. And in terms of this function, the solution of that function, the 0 of that function, you can now formulate the solutions of the general quintic. But that's not what we call a radical. And then you can ask the question, oh, but now can I write the solution of this, what do you call it, the sextic, in terms of this? And I believe that's a no. Again, I'm not an expert. I've kind of looked at, oh, what do people think about this? And I don't know, do you know more? If
No,
anyone else?
I don't know more.
And Hermite gave also a solution of the quintic by using elliptic functions.
Uh-huh.
Hermite, Briowski, many people.
Okay, thank you very much.
Thank you for listening.
Thank you. 5 minutes back.
Please. Ah, yes, yes. So what do you know about Arnold's proof?